Okay. Starting the stream. Looks like I'm 1 minute early. I'm just checking my sound. Starting the stream. Looks like I'm 1 minute early. I'm just checking my sound. Starting the stream. A little bit echo there. I think views. I feel like this is always behind. Pop out this chat, send it over. So I'll keep the chat up on top. So if you have questions, you can put them in the chat. Ask them in this window. 10:18. So what's today? Then 11:01. I'm just looking through our plans for the rest of. All right, cool. Well, I guess we could look at this in a month view. Yeah, just the month view is so awkward here. All right, so we've got some people joining in. Cool. Sorry to shift us to an online lecture format. My son does seem like he's feeling much better, but he can't go to school with a fever, so here we are online. Thanks for understanding. And so if you're just joining, we do have the chat box. You can post at any point, and I can answer questions, or questions, have discussions there. And as a reminder, we do have, here, let me get this in a new tab. I'm going to pull up our syllabus. So you can always post questions onto this GitHub page, and this is a great place to start if you have questions about like concepts or how to do homework. And especially now as we're trying to like work on our first like Python kind of project, this is a great place for like troubleshooting kind of stuff. So we can come in here. Let's look at project 2, see if anybody said anything. Oh, no, I would have thought there's something. No? Maybe 4 bar. No, I guess not. Something about the quiz. Somebody was asking about constraint equations. I thought there would be more questions about like doing project 2. But anyway, you can always put questions in here, and this is a great place to start a discussion that way. And for our work so far, right now we're kind of wrapping up module 2 work. So coming in here, let's get back to our syllabus. So we're finishing up our discussion and kind of practice on constrained dynamics, and we're going to move into constrained engineering systems. So start looking at things that have a degree of freedom where we know the forces, and we want to look at maybe oscillating motion or how fast things accelerate. But the main thing in this part is like, what is the equation of motion, and what does that tell you about how the system is going to work? So we got some time to get back to that, and today goal is finish up project number 2. So, and again, if you have any questions, pop them into the chat. I was gonna go through and show like an analysis that that I might do if this was my project, or maybe you have specific questions, like you're trying to do something and you want to know why you're getting an error, something like that. So I'll pause for a second. Cool. So we got people here. Welcome. We're running. We're doing stuff. Are you on there? No. No, just me. All right. So if I was going to turn in this project myself, first thing I usually do is just make sure everything's working, just in general. So make sure my plots work. And I think last time we were kind of changing things. So let me get this back to what it was before. 095, 025, 1, 1. And this should be 2 pi, 0 to 2 pi. Okay, so I've got three sets of geometric kinematic solutions. This first one is just telling me what the different angles are to create my 4-bar linkage system as a function of that input angle theta 1. The next one is showing me what these things look like, and if I want to look at different times, 0 is when I is 0, that means that I'm plugging in the first angle, which was 0. 360 would be back around to the same location, like once I get to, really there are, in this, when I set up this lin space, the default is that it splits it up into 50 different places, but I could split it up as much as you want. You could do 500 if you want smoother curves or anything like that. So if 50 is going to be 360, 25 should be somewhere over here. So let's try that. And sure enough, 25 is not exactly 180, but pretty close to 180 degrees, and halfway there, if we want to look at like 90 degrees, of around 12, like halfway there. And it's got to be integers, because this I is grabbing like a certain location in the solution that I've made. So now let's say I want to build some kind of 4-bar linkage that is new. Like I want to solve a problem. So one thing that I could do is look at, actually, do I have a link to, yeah, this Watt linkage suspension. So I could say this, is that the Watt linkage, I could look at a Watt linkage for maybe a, there's like a train wheel. And this will be good. Watt linkage for automobile. Do we want to do that? Or the parallel motion linkage. There we've got two things that are always moving in a parallel line. Yeah, Watt linkage could be good. So let's say I want to make a Watt linkage for like a Honda Ridgeline dimensions. So it's 79 inches wide. Well, that's because I have a Honda Ridgeline, so 79 inches in meters is 2.0066 meters. So when I'm looking at dx, this has got to be about 2 meters. Maybe I'll say like 1.9 meters, so I can mount the suspension in between the two truck wheels. Then overall, this L1 plus L2, these are going to be equal lengths, but they have to add up to at least 1.9 or more. So let's try doing, I'm going to do a little bit of some math here. Oh, actually, let me make this bigger and pop this. Oh, not like that. Turn that off. So overall, I want this distance to be 1.9 meters. This angle can be whatever I want when these two things are parallel. But let's say I want this to be maybe, I don't know, pi over 3, 60 degrees. And if that's the case, so here's my L3, here's my L1, there's my this should be L2, and this is L3. So L1 minus L2 cosine 60 degrees plus L3 should be equal to 1.9 meters. And then L1 and L3, those are the same. So 2L1 minus L2 cosine 60. And this one, oh, and then also I want to decide how tall I want this thing to be, right? So let's say I want it to be, because otherwise I can make L2 as big as I want. Like I could have like this, or I could have like that. So let's say I want this whole thing to be like 0.1 meters. So L2 sine 60 equals 0.1 meters. So now I've got two equations. So L2 is 0.1 over sine pi over 3. And then L1 is going to be 1.9 minus, or I guess plus L2 cosine 60 all over 2. So now I've got some stuff to plug in here. So this is going to be a negative 0.1 to drop it. So it's going to go over by 1.9. L1 is going to be, well, I guess I can plug in whatever I want first, right? Oh. 0.1 over np dot sine of pi over 3. L1 equals, I'll do it the fancy Python way of saying that they're equal and they're actually the same thing. So L1 is L3, which is 1.9 plus L2 times cosine np dot pi over 3 divided by, oh yeah, I want to take this whole thing and divide by 2. So now I'm setting up, oh, should use numpy np dot. So if you get an error like, hey, this thing's not defined, just double check, like, well, is there a COS function? And in this case, there's not. There's a numpy.cosine or there's a math.cosine. It's, in general, I always use the numpy cosine. It won't change the actual numbers that I get, but it does change like how useful the function is. Okay, so now all the error goes away, and I'll try to run through and see what happens. I'm getting the same kind of runtime warning that we got last class on Friday, but let's ignore it and just see what it looks like. I'm getting these weird results for theta 2 and theta 3, and what we already kind of know is that this thing can't spin 360 degrees. That would be a very odd suspension system if this Watt linkage is moving more than I don't know, 30 degrees or something. So let's come down and just look at what the paths are. And sure enough, we can see, like, as this thing tries to move around in a circle, it's dragging this hinge C into chaotic kind of places. Like, they're not random, like they're trying to follow, it's trying to solve the equation, just it can't. So what I need to do now is reduce how big of an angle I want this angle 1 to be. So I'm going to start at like negative pi over 6 and go to pi over 6. And I'll go back to like 50. And let's see. I just want to look at what's happening. And so I get a lot of good motion, but at some point it's kind of breaking. So I probably can't go to a full 30 degrees. Like maybe here, it looks like 0.4 to 0.4 works really well. So negative 0.4 to 0.4. Oh, and it's still, something's a little broken along the way. Let's look at -1 all the way at the top, because I think that's where it's breaking. Yeah, so I'm stretching it a little too high. And that's okay. We can change this down. Ooh, I don't like that one. Oh, it flipped the orientation. All right, so what's happening here is my Watt linkage is a little upside down, so it's solving for a different, it's not so much that it's a different degree of freedom, it's that there are two orientations that work, so it's like a kinematic locking between one or the other. But I can try to force it into one or the other based on, this is my initial guess for what this thing is supposed to be. So when this is -0.4, so when this thing is down here, I want L2, really I want L2 to be something like pi over 4. I don't need an exact guess for the solution. I could solve it if I wanted, but I don't need to. But this one should be roughly 0.4, something like that. So L3 should be a positive angle when this one's a negative angle, and this one should also be some kind of positive angle. So let's see what that changes. Ah, still doesn't like that. Pi over, say pi, make it like 90 degrees, or pi over 2. It did change the result some. It's still flipping it. Yeah, so it's like upside down from the orientation that I want it to be. So really I want this thing like up here. So maybe we'll just try like 0 didn't work. Theta 2. Oh. So really I want that theta 2 to be something else. So, oh, let's try this as like pi. Still, still not. I want this one to be up there. Negative. There we go. Now I'm getting like a straight line for my green line. And what I did was change. And this one, really there's an infinite number of solutions, but this fsolve is going to bring us to the closest solution. Because when you think about like, when we think about when is sine of theta equal to 0? Well, at 0 and at pi and at 2 pi and 3 pi, 4 pi. And we have the same problem here. Anytime we're trying to solve a problem with sines and cosines, there's an infinite number of possible solutions. They'll change our orientation by a little bit, but we can play around with it, kind of get to the spot that we want it to be. But now it's looking a lot better. So the path of this thing, so when I look at the last location all the way up here at the top, and when I look at the first one all the way down at the bottom, it's all moving. This midpoint of AB is moving in a straight line up and down. When I look at 25, I'm right in the middle, right kind of what I wanted it to be. Okay, cool. So now let's look at how fast everything's moving. And for the most part, like if theta 1 dot is moving at 10 radians per second, like how fast one side of the car is moving, the other one is doing about the same thing. And this theta 2 dot, how much it's rotating doesn't really matter, because in all these watt linkage suspension systems, usually you're mounted, like the wheels are mounted to the center of it, so the rotation of it doesn't really matter. It's mostly the rotation of these two bars that I care about. So that's good. They're matching on both sides for 10 radians in, 10 radians on the other side. And then for the design, it's 1.9 meters across. I've got a range of motion of 0.7 radians. So let's start quantifying some of these things. I'm gonna insert a cell below. Right now it's a code cell, so I want to change it to a markdown cell. Current design is for a bracket Honda Ridgeline rear suspension, and here I can grab I'll grab that one. Just a link to where I'm getting numbers from, right? the truck is 79 inches wide, so the suspension is designed to be 1.9 meters wide, 0.1 meters tall. Connecting link is, I'll say like L2 is 60 degrees when suspension is at midpoint. L1 equals L3, which is, and I'm just going to add 0.98 meters. So now this like helps set up, I chose the geometry, I plotted the motion and the paths, I had the speed of all those links and stuff. My own wrapping up section, now I can start talking about what I learned for this. So I had to change the initial guess for the fsolve routine to plot the paths I wanted. It worked with initial guess. Let me grab those numbers. I'm just going to make a new cell type so I can keep track of what's going on. The range of motion for this proposed design is theta 1 equals negative 0. What was it? 0.4? Sorry, I know I keep going. Negative 0.4 to 0.3. And let's do this. Rad to deg of is negative 22 to 17.2. Let's say negative 23 to 17 degrees, or 23 plus 17 is 30, or 40 degree total range of motion. And that, whether or not that's good or bad, it's just stating what I have so far. So I can say that this is good, like that's enough. One thing I can say is that I know total distance traveled, like total wheel distance that it can travel, is going to be like L1 times theta 1. this translates into, well, I guess the cosine L1 cosine theta 1, I guess I want sine, right? So if I have a 1 meter link times the sine of 40 degrees, then the total range of motion, or sine of 0.7, so 0.7 meters of travel, of vertical travel. So at least if I take like minimum, maximum, kind of take how far up and down can stuff move, it's going to be the length times that total delta theta. I guess I could write that delta, capital delta, like this. So 0.7, and then talking about like speed. Did the speed of this teach me anything? Again, theta 2, how that thing flips back and forth, I don't really care, at least in this case, but the fact that theta 1 dot and theta 2 dot are always close to each other, as the left side moves up and down at a given rate, dot theta 1, the right side will move at roughly the same rate in the opposite direction. So here, when it's positive 10, this thing is not negative 10, but it's pretty close. And then out here, right in the bulk of the travel, whatever it is, the negative 10 and positive 10 are about the same. Here we can just say plt.plot a1 comma da1, and then plt.plot a1 comma negative da3. And we can see there is a difference, because this one we're holding at a constant rate, the other one is kind of trying to follow it, but it's always within like 1 radian per second in this main block of motion. As we get out here to like higher things change a little bit more, but things look pretty good. And if I want, I could say within 2 to 3 radian per second. So that's what I wanted to show, at least for today, of like how to wrap up this assignment, is take the work that you did and how you did it, kind of document your process. Like, okay, here I'm talking about Honda Ridgeline. I put in a link for it. That's how I chose what these dimensions are. And then I had to change things around to get it to work the way that I wanted it to. And now I'm like summing up what was good about this model, or why would I use this model? Why go to the next step of like building a CAD model or something? Okay, so I've been rambling for a while, and I mean we still have people here, so that's good. You might be on a different tab, but you're here in the live stream. And I haven't seen any questions pop up here. Do we have? Yeah, nothing new in our GitHub discussions. So if there's nothing else, I'll hang out for a little bit. If there's no other questions, then we can wrap up. And then we'll be back in the classroom on Wednesday working on Module 3 on the next step, bigger and better. Well, I guess not bigger, not better. It's good. Good changes. Demonstrate some learning and then move on to the next thing. Pop this open a little bigger so we can see all of that. But at least this would be my like wrapping up section. Like, what did I do? How did I do it? Why did I do it? Those kind of questions. Nothing in the chat. Okay, if there's nothing else, then reach out. Don't forget, we have our don't forget about our discussions. This is a great place to go, especially as we're trying to deal with problems here. Like if you have an orientation flipped like that, you can copy this image, paste it into a new chat. Here, Q&A. Paste it right in here and say like, hey, this is the orientation that I have. This is the orientation. Well, right now it's what I want, but if it's flipped upside down, like what's going on? Why is this not working? And then we can jump in there and say, hey, what did you use for these? What were these inputs for this XSOL? Because this is going to be the first solution that it's trying to solve for. Thanks, Marcel. So yeah, don't forget about GitHub discussions. Great place to get answers. And I'll see you on Wednesday.